to last week. Well, Monday. Everything we've done up to Monday is actually this beam only. Okay. Everything we've done so far is for fully restrained beams. Okay. So generally for steel beam design, there are two types. One is fully restrained beams, whereby no lateral torsional buckling occurs. So this is what we have done so far. All right. Therefore, from today onwards, we are going to tackle the other type of beam, whereby it is semi-restrained. In other words, there will be some lateral torsional buckling that will occur. Okay. So that's the difference between the beam that we've covered and the beam that we will cover today. Okay, so today we'll cover the semi or partially restrained beams. Okay, so for that you need to skip. So for that you will need to skip to slide number 11. So the slides that I shared with you earlier, I told you before, it's not complete. Okay, so I have a new set of slides now, which is complete for beam design. All right, so I will share this slide with you. You can delete your own slides. I shared with you earlier for fully restrained investment. Okay, unrestrained or semi-restrained beams. Okay, so for this one, let me know if you cannot see my slide. I'm showing slide right now. If it disappears, you let me know. All right. Okay, so like I said, there's another type of beam which is unrestrained or semi-restrained beams. The formula for these beams are very similar, actually, very similar to the fully restrained beams. You can see the capacity. This is the capacity, yeah. This is the capacity. So the capacity is same, Wy times Fw divided by gamma M1. Okay. The other formula, MCRD was W times Fy divided by gamma M naught. Okay, this was this was the previous formula that you used. Okay, now if you look at actually W, let's look at W first. W for Wy is actually WPLY for class 1, class 2 section, and WELY for class 3 section. It's actually the same. It's actually the same as the previous formula. Okay, multiply by Fy divided by M1. M1 is 1. So actually, all of this same or similar. Yeah, similar. Similar to the previous formula that you used. Yeah, similar to this formula. Okay, very similar. The only difference now is we have a new term. This XLT, this is the only new thing in this formula. Okay, XLT. So what is XLT? I circled down there. XLT is the reduction factor for lateral torsional buckling. So basically what it means is, if your beam is fully restrained, so maksudnya, if your beam is fully restrained, your moment capacity is W times Fy divided by gamma M. All right. Now, if it's semi-restrained, sepatutnya partially, but never mind. Yeah, but if it's semi-restrained, okay, you have a gamma LT here. times W times Fy divided by gamma M. Then, if it's semi-restrained, you have this reduction factor. Okay, so if it's semi-restrained, you have a reduction factor to reduce the MC. All right, so if it's fully restrained, you get a full moment, you get a full strength. But if it's semi-restrained, you need to apply a reduction factor to reduce the strength. Basically, that's it. Itu saja perbezaan dia. Okay, but this is a big difference. This is a big difference. Later on, the following slides, you will see the big difference. Now, when I say fully restrained, semi-restrained, I need to explain again what I mean. Okay. Let me delete everything first. Erase all. Okay. Okay. Let me explain again. So the previous formula, you can only use for fully restrained. What does fully restrained means? It means if your beam is like that, right? So this is your beam in 3D. That's your I-beam in 3D. If it's fully restrained, that means the compression flange is restrained. There is something clamping. You can think about it in this way. There is something that is clamping your compression flange from moving sideways. So now, if your compression flange wants to move sideways, it cannot move sideways because there's something holding it there. Example is, if this is your beam, then you have a slab on top like this. You have a slab sitting on your beam like that. If you have a connection detail like that, then obviously that flange cannot move. The compression flange cannot move because you have the concrete stopping it from moving. All right, now compare it to a detail like that. A beam like that, carrying maybe a floor, a wooden floor. Now, if this floor is not connected to that beam, the floor sometimes is just sitting on the beam. It's not connected. Yeah, you can do it that way. So if that floor is just sitting on the beam, no connection at all, the beam can slide. The beam can slide sideways, left and right, if you want to. Yeah, so the beam can go in this case. So in this case, it's unrestrained or semi-restrained. Okay, that means your beam in 3D so that means your beam in 3D, there's nothing holding it. There's nothing clamping the compression flange from moving sideways. It can move sideways. So the compression flange can move sideways once the beam gets loaded. Okay, so this is semi-restrained. So you need to know the difference between the two. Okay, so any questions between fully restrained and semi-restrained? Or you know what it means now? Faham?
Yes, clear.
Okay, all right. Okay. Okay, so back to the formula. Okay, so if it's unrestrained or semi-restrained, this formula you use. The only difference in this formula is the XLT. Okay, that's the only new thing we are introducing to this formula. It's a reduction factor due to the lateral torsional buckling effect. Okay, now this looks simple. It looks like, oh, just one term. Okay, but it's actually very complicated. Where you get this term, it's actually a very long story. Okay, so where does XLT come from? You need to go to the next slide. There, that's the formula for XLT. That one, the one that I just circled. All right, XLT, the formula is 1 divided by That is theta. Yeah, so the formula for XLT is 1 divided by theta LT rotation, yeah, plus square root theta LT squared minus theta alpha LT squared. But it cannot be more than 1. That's the formula. That's a crazy formula. Okay. Now it gets more complicated. Okay. So the next question is, okay, on this formula, actually everything we don't know. So normally when I answer question, normally when I do test question, exam question, I ask myself, what are the terms that I know? What are the terms that I don't know? All right. So in this case, unfortunately, all the terms is unknown. Okay. Okay. So what is alpha LT? Now alpha LT is 0.5 times 1 plus, sorry, theta. So theta LT is this formula here. So you see I've drawn red arrows where you get the different values from. Yeah, I've drawn red arrows to link the formula. So alpha LT is the term below here. Not alpha, theta LT is the term below there. Yeah, that I've just highlighted with an arrow. It's 0.5 times 1 plus alpha LT times lambda LT minus lambda LT dot naught, different, close parenthesis, plus beta lambda LT squared. Okay, now, in this formula, there are still things that we don't know. So you see, it gets deeper and deeper. To get this, you need this formula. But for this formula, you need to use another formula. For this formula, you need to use another formula. It keeps on going to another formula. Okay? That's why you're going to notice in this pattern. Okay? So, for this formula, beta is 0.275. Lambda LT naught, normally we use 0.4. So at least, okay, 2 of them is fixed constants. Okay? Beta is 0.75. Lambda LT naught is 0.4. Okay, at least 2 of these are fixed. Okay, these 2 are fixed. Okay, so now the only thing that's left that we don't know is alpha and lambda LT. Okay, alpha is here. Or sorry, rather alpha LT. Alpha LT is that table. Okay, so alpha LT depends on the type of cross-section that you have. If you have rolled I section, then you use the first row. If you have angles like that, then you use the second row. If you have welded sections, then use the third row, and so on and so forth. Okay? So normally, you will notice in my test questions, so don't worry, in my test questions, I always give you, in my test and exam questions, I will always give you a rolled I section. So you only have to focus on the first row. Okay? In my test question, you notice I always give you this type of question. I roll I section only. All right. So you only have to follow. So you've only need to follow the first row. Okay. But even then, the first row, you have choices. H over B less than 2, you use buckling curve B. If it's more than 2, less than 3.1, then you use C. So H over B is basically height divided by the breadth or the width. Okay. So if your beam is not that high, so if the height versus the width is not that great, less than 2, then you use B. If it's greater than 2 but less than 3.1, then you use C. Okay. Once you decided whether it's B or C, then you go to the table below. Let me delete everything first. So once you've decided whether yours is whether it's B or C, then you go to the table below. Then you can get your alpha LT, whether it's B or C, 0.34 or 0.49. Okay, so everything in that formula, in this XLT formula, we have already established except one. There's one more that's missing. Gamma LT. No, lambda LT, this one. So everything in that formula we have already except lambda LT, this formula here. This formula here. Okay, what's lambda LT? So lambda LT is square root WY times FY divided by MCR. Now, WY is your WPL for your beam. The one that you use for your restraint design. Yeah, to calculate MC, it's WPL times FY divided by gamma M. This formula, you should remember? Yeah. So same W times Fy, same Fy divided by MCR. So the only thing that you don't know. So basically, in this entire page, the only thing that you don't know now is MCR. That's the only thing you don't know. MCR. So what is MCR? Another formula. That MCR. This is the formula for MCR. It's C1 times pi squared EIZ divided by L squared. The whole thing multiplied by square root IW divided by IZ plus L squared times G times IT divided by square root EIZ. Everything we know, most of the things we don't know. L is basically the distance between the point of restraints. E is given, is fixed, 210,000 Newton per mm squared. G is also fixed. So E is fixed, G is fixed. Okay, you just use these figures. IZ is the second moment of area about the width axis. Now, this from your section table. I is the warping constant also from your section table. IW is the warping constant also from the table. Okay, so everything here you know. Okay, the only thing I need to explain a little bit is L. What is L? What exactly do you mean by L? It's not the beam length. So that's your beam. Again, that's your beam. Okay, now that's your beam. Now, if your beam has some sort of restraint, but it's semi, so this L is applicable if your beam is semi-restrained. Okay, so let's say I have some sort of restraint in the middle of the beam and at the end of the beam. Okay, let's say my restraint condition is like that. Okay, I have some restraint at the ends, I have some restraint in the middle. So basically what that means is anything in between, that length there, that length there, that length there, that length there, this is unrestrained. That is the L you want. It's basically the length between the restraints. Okay? Now, if your beam is like that, if your beam is like that, you don't have any restraint at all. No restraint. Maybe some restraint at the end. Maybe some restraint at the end. But no restraint in the middle. Now your L is this one. The full length of the beam is the full length of the beam. Okay? It's basically the length between the restraint. That is L. Okay? So that's L. So L, you know, E is given, G is given, I, IZ, IT, and IW you get from the table. Everything you know in this formula, except one. I highlighted it as well. C1. What is C1? C1 is the only thing that we don't know in this formula. So then we go to the next page to figure out what C1 is. See, that's the problem with this lateral torsional buckling. You need to use a formula to find there's always new formulas to find what's missing from the previous formula. Okay, so there's formula on top formula on top formula. Okay, that's what makes this a little bit, it's not difficult lah, but it's hard to remember. Okay, back to the topic. So what is C1? C1, you need to look at this table. So C1 depends on the shape of your bending moment diagram. If your bending moment diagram is the normal parabola with simply supported ends, then C1 is 1.127. Right? Which is normally the question I give you. Normally the question I give you is like that. Yeah. A normal parabola with no moments at the ends, simply supported ends. C1 is 1.127. Okay. Okay, now, if your beam is continuous, or if you have fixity at the ends of your beam, that means you have moments at the ends of your beam. Like the second case. Second case, you have moments at the ends of the beam. Therefore, C1 is now 2.578. Right? Now, next, if your beam is point load, then you have a triangular bending moment, then it's 1.348. If your beam has point load but has moments at the ends, then it's 1.683, your C1. So that's your C1. Okay. So now basically that's it. Okay. So now I'm just doing a summary of exactly how you design a semi-restrained beams. The first step is you need to draw the bending moment diagram. Then you need to determine the Fy. But now, actually, for your restrained beams, you already done this. Okay. So this tool is the same thing that you do for the fully restrained beams. Okay. You should know how to do this already. Okay. So the next thing, the thing that is new to lateral torsional buckling, semi-restrained beams are steps 6 to step 10. This is the new stuff. So you need to work out the effective length or the unrestrained length. It's the same thing. Okay, you need to work out the unrestrained length. Or some people call it the effective length, else, but basically it's LCR. Okay. Now, next, you work backwards from my slide. You go to the last slide. You calculate the last figure first, MCR, because you need it to feed it into the previous formula. Yeah. So, step 4, you work out the MCR. Once you have the MCR, then you can work out gamma LT. Once you have gamma LT, you can work out alpha LT. Once you have alpha LT, then you can plug everything into your MCRD formula and you can calculate the buckling resistance. Okay. So basically, the actual calculation, you have to start from the last slide here, this slide. From this slide, you find out what C1 is. Once you have C1, you go to the slide before, you put C1 in here, you calculate MCR. Once you have MCR, you go to the previous slide again, you calculate what is alpha lambda LT. Once you have lambda LT, then you can calculate XLT. Once you have XLT, then you can come in here and calculate the buckling resistance, MBRD. This is the bending resistance due to LTB, lateral torsional buckling. Okay. So once you've done that check, same. The last check is the same. It's this check. You have your moment from your bending moment diagram over your MBRD from the top. This thing here from the top. Okay. And that's basically okay. So yeah, so that's basically for semi-straight. So on next Monday after the test, I will go through an example of this with you. Okay, so next Monday we'll go through an example. At the moment, it looks very confusing because you haven't tried to use it yet. Okay, so next Monday, once we have had a go at an example, hopefully everything will be clearer. All right. Okay, so that's it for today's class. So just a short class. I just want to go through the theory with you so that Monday I can go through example with you. Okay. Before I end the class, I will just want to tell you something about the test. So for Monday's test, I just want you to be mentally ready because Monday's test doesn't include this. So for Monday's test, we stop at page 10. Okay. So Monday's test, we start at page 10. Everything after page 10 is not included in Monday's test. All right. So that's one thing about Monday's test 1. The second thing about Monday's test 1 is you will not have access to your phone. Okay. So I will give you the question paper. I will print out all the questions on the question paper. So bukan lagi macam RCD ya. Okay. So bukan lagi macam RCD. I will give you the questions on the question paper, and then you need to answer it without referring to your phone. So you have to get ready. I know there are differences. That's why I'll let you know earlier. All right. Okay. So before you go, let me just do the attendance. Any questions about what I taught today? Or do you want to wait until we do the example first, then baru you ask? Any questions you want to ask, you can ask now.
No, so clear, doctor.
It's okay. All right. Once we do the example, then it'll be clearer next week. All right. Thank you. Okay. Wait. Let me attendance. 1 second. Okay. Okay. You should be able to see the attendance screen now.